Okay, we're going to be talking about the concept of regression. Regression is linked to supervised learning. Supervised learning, we know how that works already, so I'm not going to basically baby you on that one. But how it's used is basically to predict, which is what we're looking at with supervised learning predictions, a continuous output based on different input features. So when we've been looking at supervised learning in the past, we've been talking about individual aspects like, what is this? It goes into the system. It goes, oh, it is a circle. But you can appreciate supervised learning can actually make things more complicated and have several inputs being fed in all at the same time for it to give a more complicated prediction. So let's imagine that we had being fed into the system something which looked like this. And let's imagine that this would be an input, this would be an input, this is an input, and this is an input. And let's imagine that we trained it and it predicts it is a picture of a house. Even though these are all separate shapes, it's using all that information to create a prediction. So several inputs. Regression's job is more or less looking at what's being fed in, and it looks at what similar patterns has it seen before to give that prediction. I will give you an exam definition at the end of the video, but what I'm going to do is explain this using probably more concrete type examples rather than this basic overview. So supervised learning is simply using an algorithm which looks at to learn X to Y, or input to output, which are mapped together. So the output, I'm going to put output label. So basically there is a mapping between the input we put in and the output label where supervised learning works by us giving the correct answer to the system using lots of data, so lots of training data. So we train it up with the correct answer over and over and over again with different variations, and it'll learn through. So it needs the correct label Y for the input X given. So previously we've looked at really simple examples with fruit, but we're now going to take it to the next level in terms of understanding. By having this correlation of these learning pairs or matching pairs of the correct output label matching the input, eventually we won't need to, when we're training, give it the output label. We just give it an input by itself and it should be able to give us the correct output. Imagine if I was to simplify it, we were to do this, and this isn't the most accurate representation, but it should get you to understand. If we're going to be training 2 + 2 = 4, and we give this over and over and over and over again to the system, eventually we should be able to say to the system, what is 2 + 2? And it should be able to give its own output of 4. Obviously this example won't work because it's not looking at any variations, etc., but I'm making the point that when you're training it, you have your input and you have your output labels, or your Y and your X, and they're matching pair. You train it with lots of data, and eventually you won't need to give it the output labels. You just give it any input and it'll give you the output itself, the correct answer. So what does this look like in reality? So we're going to be looking at a scenario for house price predictions. What we have with the X's are data. This data is historic data of different houses which have been sold. So for prices in $1,000 on this side, and our input data here is house size in square foot. So we can see that these are the different houses. So a house which, based on our data, is below 500 square foot is sold at 100. Yes, I'm not going to be using this. I'm just going to be using 100, 200, 300, 400. Whereas a house which is slightly bigger, quite naturally, based on the size and square footage, is going to be sold for slightly more. So the red X represents the house itself and how much it was sold for against the house size in square foot. So let's imagine that somebody comes up to you and they say to you, like a friend, how much am I going to get for my 750 square foot house? Guess what? We can use our model to give them an estimate. So what the model will do is it'll put a straight line through the data. We call this the regression line. So this purple line here is the regression line. So this looks at the relationship that our models learnt between our price and our house and feet, or the house feature, our input, and our output. So the house feature in this case is the house and feet. And then what our model will do will be to join up the axes. Ooh, let me do a different color by creating a line to the point. This is a really inaccurate representation, but never mind. And let's imagine that the house would potentially be sold for like 190 based on using our regression line and joining up where 750 would be on our input, and it'll give us an output of 190. And we call this method linear regression. Really simple. You draw a line of best fit through the data. You then, well, going through the middle of the data, shall I say, you then join up the axes of where they should meet based upon your input. It will then give you an output. So picture this. We're using our AI model. We don't have this 190 as an output. So we type in the 750. Remember, this is data which has been trained already. We type in our 750 as our input. The model then will predict the 190 an output, and that's only because of lots of training. The training would have come from us training the system, saying that normally a house, which is, let's say, I'm going off the screen, 400 and let's say 90 square foot or square feet, is around $80,000. Is it around that? Then what would happen is we plot in our other data. So remember, this is our input, this is our output. Our output is going to be labeled. So we tell it when it's 490, it's going to be 80,000. So we've got our matching pair, and we keep doing that for each one. We give it an input, we label the output, we tell the system, then the system will be able to cope with any other type of number because it's got enough data to work out the relationship based upon this linear regression. So there's another type of regression we could use as well. That would be a curve. So let's have a look at what that looks like. I'm going to do that in a different color. Let's do, why is it not letting me change my color? There you go. Perfect. So let's imagine the curve would look like this. So when we use the 750 again, in terms of square footage, is actually closer to 250 rather than what we had before, which is 190. So it's another way we can train our model. We can train it using linear. Oops, I've got off the screen. So linear or non-linear. Let's talk a little bit about non-linear now. Think of it like this. When we're using linear, there's a a reality, a relationship whereby where the square footage goes up, there is the same increment in terms of price increase. What I'm saying is that if it goes up every X, it's always going to go up in square footage, in Y the same amount. But we know that in real life that isn't actually the case with square footage of house. So think of it like this. If you are buying a house in a small area, and it's a small house on a street, and this is like house number 1. House number 2 on the street is quite a bit bigger. These are chimneys, by the way. We would know that the price of this house 1 is going to be lower than the house of price 2. So let's say 200,000, let's say 800,000. There's going to be a substantial increase. But when you get to like the sizes of mansions, the price increase isn't going to be as substantial for the square footage. The square footage is already huge as it is. So the increase between house 3 and 4 is not going to be as much. It might be 700, and let's say 750. Whereas if we were going from house, actually 800 here, so that won't work with it. So let's do 1,700, and let's do 1,750. The price between house 2 and house 3 is huge. Now you normally, let's imagine that we had an intermediary. So let's imagine we had another house here which is slightly bigger than 1 and just a little bit less than 2. So let's say that this is going to be for 400. My point being is that if you treat this as simply a line like that, which is fixed, it doesn't really match it to real life expectations, because there could be other variables which brings us down. Whereas with a curve, we're basically saying that yes, there is an increase, but it'll soon get to the point where it won't make too much of a difference. It's kind of like leveling up in a game, where I would argue if you are a character in the game and your stats to begin with on like 0 for your character, and you upgrade it and you grind and grind and grind, and a few weeks later your character stats are 1,000, the difference between that and that is going to be huge. But when you get to a certain point in the game, the amount of strength you can have, for example, whilst you can keep increasing it, isn't going to make that much of a difference to you as a character. You're already at such a high strength already, you can kill things with a couple of blows. It's not going to mean too much. Going back to this example again, what is it that you need to take away for your actual A level? A couple of things. Number 1, supervised learning uses what we call regression. Regression, it allows us to predict a number infinitely many possible outputs. So once we do our training, we can put in, I want you to tell me how much a house would be for 1600. That will be our input, and it will be able to give us another possible output because of this, even though it's not in the training data already. You need to be aware of a concept called linear regression. Linear regression is really simple. It is chosen to be used when there is a straight line correlation between variables. So when it's always going to be you can almost say a fixed correlation, where it's always going to increment in a certain amount at each phase, versus, let me just put non-linear up here, and where do we use that? When there is correlation, but it is not linear. Okay, so basically, let's give some examples of linear versus non-linear regression models. I'm not going to go through every single one, but I'm going to do a few. So let's do salary prediction. So if we had, let me make this a bit smaller. Chart, and let's imagine that we had years, so 0, 1, 2, 3, and let's say we have 50,000, 60,000, 70,000, 80,000, and let's say that we have, if you're working for 1 year, 2 years, and let's say your 3rd year, we do our regression line. Really badly drawn, I apologize. If someone's to say what's going to be the 4th year, you'll be able to mark it quite accurately. Salary increases are normally predictable with the years of experience you have, so linear is really easy to use in that regard. In terms of fuel efficiency, it'll be the same. You have a relationship between, instead of years, you would have the engine size, and you'll have fuel. And normally, the size of the engine, ignore 1, 2, 3, 4, but you get the gist of this. You'll be plotting it, it'll be fixed. That line would normally be a straight line, because each increment, in terms of engine size, would normally give a set constant pattern for the amount of fuel it needs. We looked at real estate before. You could say it's linear if it's really at a really basic level based on those inputs, but you could also argue it'll be non-linear as well. Education outcomes, where you have grades versus, or scores versus the hours of study. Again, you could argue there's lots of other variables involved, which is very, very true, but from a basic system, you could potentially plot it if you've got lots of data and people have all studied the same way. So if you've done a study and everyone studied the same way, you force them to study the same way, you probably see a correlation. And credit scoring is another. If you look at weather forecasting from a non-linear perspective, it's really challenging. So I've managed to find this chart here. We've got the blue points. The blue points are the data points. This data simulates basically what temperature is being recorded on a given day historically. The red, as we know, is the regression line or the trend line. In this respect, it's not the straight line. It's not the non-linear straight regression line. It's more of a trend that we're looking at. So from this, we can see that there's patterns. It doesn't necessarily equate to it's going to be completely accurate, but it appreciates that you could find patterns from this. Whether, as we know, when it comes to temperature, it often does follow like a cyclical pattern. That's basically down to like the rotation of the Earth, conditions in our atmosphere, etc., seasonal changes. But we also know it's complex. We know that there's a whole range of different variables or different inputs, we can say, which has an impact on the results which we've got. Because it's a variable rate of change, when we create a model, we're not going to be using, obviously, the linear straight line. we're going to be appreciating that we're going to need a non-linear line because of how random some factors could potentially be. But if we were to say, okay, what's the temperature going to be like on the, let's say, I'm trying to find a day which, okay, let's say the 11th. Actually, let's do the 31st of the month. So hold on. If we would do 31st, there we go. Being plotted here. Why? It basically looks at the previous data and it makes a prediction based on the trend that it will be around this area in terms of temperature. Is it going to be completely accurate? No, but it does take into account other aspects. Okay, so I'm hoping you've got an idea now of, if we say, a non-linear regression model versus a linear regression model, and what regression actually means as well, and that it's used in supervised learning. I've given you these as examples, but the likelihood of them asking you for an example is not that high, but we may as well be fully ready to cover that. So remember, with nonlinear, it looks at variable growth, it looks at dynamic growth, it looks at the ability to handle trends rather than a fixed rate. It's a variable rate of change.